Okay, so we'll now look at memory management. As we discussed a few classes before, the operating system's main objective is to manage resources, and memory is one of the most important resources present in the computer, right? So it needs to find efficient ways to manage memory. Okay, so we'll build up into what problems can arise when you're managing memory, right, and how current day operating systems essentially handle such an issue. Okay, to start off this, let's start with this famous with this program. We've seen this a couple of times. We have a small program written in C, which essentially just prints hello world onto the screen, right? And what we do is we compile this and get an executable. If I compile it with this particular compiler, GCC space hello.c, which is essentially the file name, I would get an executable called a.out. Now, to run this executable, I execute ./a.out, right? Now, executing or performing this operation ./a.out essentially creates a process, right? And what the contents of this process essentially, as we've discussed earlier, would essentially have the code section, right? Or it's often called the text, right? So so code essentially are instructions comprising of the various functionality of the particular program. For instance, the main function and the instructions that correspond to the main function would be present in the code area, right? Very closely related to the code are the libraries, right? So there are multiple different libraries that are that may be present in your process, right? So one of the most default libraries is called the libc or glibc, and most standard functionality of your programs such as printf, scanf, fopen, fclose, and so on would essentially be part of this libc library, right? So the libc library is also comprises of instructions, and therefore it is also code, but we just consider it separately in this particular slide for a reason which we will which becomes apparent as we progress, right? Now, so we have this part over here which comprises of the code areas, the code part of the program, as well as that of the libraries. So what really happens is that the code gets loaded in small chunks into the processor, and the processor executes the instructions present in the code and libraries, right? So also present in the process is the data region, which comprises of the global data, a stack which grows from the higher address to a lower address, and essentially comprises of holds the local variables present. It would hold also some metadata, some important parameters for the process execution, um, such as frame pointers and also return addresses, right? Now, if your program uses malloc or dynamic allocation, then your process also has a section known as the heap. So all of this, right, the code, the libraries, data, stack, and heap should be present as part of your memory, right, the DRAM. So coming back to this, right, so we have the processor, and it has various output, various pins at the output, and important set of these pins are the addresses and corresponding data pins, right? Now, as we've seen in the previous videos, everything within a computer system has an address, right? And we essentially looked at this memory map, right? So similarly, when you're actually running a program and you create a process, there are addresses associated with each part of it, right? So the libraries would have an address, the code regions would have an address, each byte of data would have an address, and so on, right? So up to a byte level granularity, each location or each byte within the process would be uniquely identified by an address, right? And as we know, this entire process is going to be or reside in memory. So this entire process is going to be mapped into this region of the DRAM, right? So, what you would immediately see is that because it's mapped into this particular region of DRAM, and the DRAM is in the range of 0x80 million to 0x90 million, therefore every address within this particular process should fall within this particular range, that is 80 million to 90 million. Okay, so so based on how the process executes, I could have let's say my code starting at say 0x80 million, or my data starting at let's say 0 like here 0x80 81 million and so on. Okay, but this essentially brings out two challenges from a programmer perspective. Okay, the first challenge is, as many of you would have guessed, is the aspect of insufficient memory. Quite often your process may require considerably large amount of memory, much larger than the available DRAM, right? So just to give you an example, suppose I go back here and suppose I essentially create a program where I define an array which is, let's say, larger than 256 megabytes, right? In such a case, my entire DRAM, which is only 256 MB, would not be sufficient, right? So the problem that arises if we actually do such a mapping is that we may soon run out of memory, at least the memory present in our system may not be sufficient to support large programs or large processes, right? So we would have insufficient memory. The second problem that we would essentially see is the aspect of incompatibility. So as we discussed in the previous class, these memory maps that we see over here are unique to a system, right? So what it means is that if I have, let's say, one particular computer, I may have my DRAM present at say 80 million and extending to 90 million, right? On another computer, my DRAM would first of all be larger or smaller. It may start at a different address altogether, right? So now there is going to be a problem. So if I compile my program for a particular computer, what I do know is that all the addresses would be within the range of 80 million, right? And this is so because this particular computer has my DRAM mapped to this between 80 million to 90 million. On the other hand, if I essentially take the same executable and try to run it on a different computer where, say, the DRAM starts at 90 million, the address 90 million, the program will not work, right? Because the memory map is different, and at 90 million we do not have any memory present, right? And therefore the code, data and so on cannot be essentially stored, right? So this kind of mapping, right, where we essentially map everything to our region of DRAM, first of all, it could lead to insufficient memory, but also the aspect of incompatibility, right? As we say over here, a program compiled for one computer may not execute on another computer with a different memory map, right? Now let's see what else could happen due to this kind of mapping a particular process directly to a memory. Okay. Now one thing we spoke about in earlier videos is the aspect of multitasking. So what we did mention is that we have a single processor like this, and this processor essentially executes, and its execution time is essentially multiplexed between various processes, right? So here, for instance, we have 4 processes, process 1, 2, 3 and 4, which essentially time multiplexes or shares this single processor. So what we essentially see from here is that process 1 executes for some time, known as the time slice or time quanta. Then there is a switch and process 2 executes, then process 3 executes and so on. Okay. So what does this actually mean from a memory perspective is the fact that all the processes that are currently executing or multiplexing the CPU should essentially reside in the memory, right? So here we have one memory, one DRAM, and we have process 1, process 2, process 3 and process 4 essentially residing or getting stored within the DRAM. So it should be noted that each of these processes have their own memory map, like their own code, data stack, and so on. Process 2 also has their code, data stack, and process 3 and so on. Each of these is essentially independent. Okay, and all these processes are essentially sharing the DRAM that is available on the system. So what could go wrong with in such a case? Due to this type of multitasking environments, um, the okay. So due to this type of multitasking environments, we essentially have the problem of isolation, right? So let's say one of these processes is essentially a web browser where you're essentially logging in through your bank account. The other one, the other process may be something like a gaming application and so on, right? So both your banking application which you're running on your browser and the gaming application are both residing in your DRAM, right? And it is very critical for the data of process 1 should not be accessed by process 2 and vice versa, right? And why do you need this? Because you do not want process 2 to interfere with the execution of process 1. You do not want the data of process 1 being leaked out to process 2 and so on, right? Process 2, if such isolation is not present, then process 2 could tamper or hamper with the execution of process 1 and so on. So what we really need is the fact that all these processes which are essentially multiplexed on the processor should be isolated from one another. Okay. Now there is also the need for shared libraries, right? So when we took this example, we mentioned that here we have a printf function. Now printf, as we mentioned, is essentially part of this libc library and is going to be present in this library part of this entire process, right? But what you'd also know is that there would be many processes, many applications that are executing on your system which are also using the same printf, right? Now the issue that can crop up is that if printf is used in all of these processes, then a copy of this printf code, in the other words, the copy of this library, would also be present in every process, right? And this is going to be very inefficient, because if there are, say, 4 processes running or on a system at a particular time due to the multitasking, and each process uses this printf, then you would have 4 copies of the library going to be present on your system or in your DRAM, right? Now this is inefficient because you don't require 4 such copies. It is the same code, and therefore just a single copy of this printf function is enough, right? So in other words, when we're using these libraries, or these shared libraries as we call it, these libraries should be shared, as the name suggests, across the various processes. So if I have 4 processes in my DRAM, I want that there should be only a single copy of the libraries that are present, or in other words, a single copy of the shared libraries that are present, right? So this is another problem, that's another challenge that we need to solve, right? And of course there is this third point, that we have this one DRAM and somehow we need to share this DRAM across multiple processes. Okay, so let's see what current computers do, right? So yeah, so right, so before so current computers essentially make use of something known as virtual address spaces, right? And I would also like to highlight over here that prior to this concept of virtual addresses, there were a large number of different techniques that were used or tried out and so on among different computer systems, different operating systems, and like over several decades. Some of them were efficient, some were not efficient, and so on. Current systems essentially make use of this concept of virtual addresses, right? So what is this aspect of virtual address, right? So with this concept of virtual address, each process now owns an entire contiguous range of let me just check what's the next. Yeah, each process now owns a contiguous range of addresses known as the virtual address space. So, on a 32-bit platform processor, for instance, each process would have a virtual address space starting from the address 0 to a value of 2 power 32 minus 1, right. So, any address within the range of 0 to 2 power 32 minus 1 for this process would be essentially within the virtual address space of the process. Okay. Now, what does this mean? So, when my program executes, essentially it would be accessing various instructions, it would be reading and writing data, it would be accessing the stack and global data and heap and so on. So, the CPU only works within this virtual address space, right. So, the addresses that essentially are emitted out from the CPU is essentially of the form of a virtual address. So, again just to highlight, if I have two processes, for instance, there would be two such virtual address spaces. Each virtual address space ranges from 0 to 2 power 32 minus 1, right. So, the virtual address emitted from the CPU now gets translated by something known as the memory management unit or the paging unit into what is called as a physical address, right. Now, this physical address is essentially your DRAM and is going to get mapped into this 256 megabyte region in this particular case, where the DRAM presence is present. Okay. So, how is this beneficial, right? So, before we go into the details about how it is beneficial, we will essentially see a little more about how this entire thing is mapped, right, how it essentially works. For now, what you would need to understand is that each process has a virtual address space, and each virtual address space is this contiguous region of addresses from 0 to 2 power 32 minus 1, right. So, let us get a bit more deeper into how this thing works, right. So, in this concept of virtual address space, my entire process, right, is split into or is divided into fixed size blocks known as pages or blocks, into fixed size blocks typically of 4 kilobytes, right. So, just to go back here, I have my virtual address space for my process ranging from addresses 0 to 2 power 32 minus 1, and it is now split into fixed size blocks of 4 kilobytes, right. So, here in this particular case, I am just showing 6 such blocks. Each block is of 6 kilobytes. Now, your DRAM similarly is also now divided into what we call as page frames, and each frame, a page frame, is also typically of 4 kilobytes, right. So, we have the DRAM divided into page frames, your virtual address space divided into blocks, right, and now there is a mapping between the virtual address space of a process and the corresponding page frame in the DRAM, right. So, this mapping is essentially done with this kind of a table over here called the page table for a particular process. So, this example shows it is very simple, because what we say is block number 1 of the process is mapped to page frame 1, right. So, block number 2 is mapped to page frame 2 and so on. But this mapping does not have to be one to one like this, right. It does not have to be sequential and in order as we see over here. We can even because we are having this mapping at a granularity of 4 kilobytes or 1 page, we can essentially perform the mapping in any order that we want, right, as long as we essentially maintain this process page table. Now, in this example, for instance, we have block number 1 which is mapped to page frame 14, block 2 mapped to page frame 2, block 3 mapped to page frame 13 and so on. Okay. Now, how does this essentially work, right? So, yeah. So from my what my CPU sees is the only the virtual address space, and as we have seen in the slide below, that the virtual address space essentially comprises of blocks of 0 to 2 power of 4 kilobytes. So, the entire range 0 to 2 power 32 minus 1 is split into 4 kilobyte blocks, right. Here we have this memory management unit which takes this virtual address which emitted by the CPU and uses this process page table to map this virtual address to corresponding physical address, right. So, for instance, if my CPU puts out a particular address which happens to be in, say, block number, where is it? Yeah. If my CPU puts out a virtual address which happens to be in block number, say, 3, then my memory management unit would look into the into the table, the process page table, and identify that block number 3 or for this particular process is mapped into the page frame 13, right. And using this, the physical address gets created. Now, page frame 13 would be within this particular DRAM, and therefore the data or code can then be accessed, right. Now, let's see how this essentially benefits us. So, the thing that essentially we take care with this is the aspect of incompatibility, right. So, with this concept of virtual address space, we are able to handle the incompatibility issue, right. So, now when a programmer writes code, when a programmer compiles the code, the compiler generates an executable assuming that the region of memory that the program would execute in ranges from 0 to 2 power 32 minus 1, right. That is the virtual address space. The compiler the programmers do not need to bother about whether there is only 256 MB RAM or 512 MB RAM or 1 terabyte RAM. It does not have to bother about where in the entire memory map these these RAM regions are mapped, right. It only it generates a code, the programmer writes the code and the compiler generates the code assuming that the entire region ranges from 0 to 2 power 32 minus 1, right. So, any program that is written and compiled would be in this particular range of 0 to 2 power 32 minus 1. The operating system and the hardware makes use of the fact that the memories could be at different locations, it handles the different size of the memory and so on, right. So, in other words, if I write a program and compile it for one particular computer, this program would work almost seamlessly in any other computer as well, with a different memory map, with a different size of DRAM and so on. Okay, done this. Okay, so so this concept of having this concept of having a virtual address space for a particular process and then using the page frames and blocks of memory and a process page table to map a particular block in the virtual address space to a corresponding page frame can be extended to a multitasked environment, right. So, if I have multiple processes running, so in this case process 1, 2 and 3, the same concept can be extended, right. So, in such a case, we have each of these processes code and data and the space split into blocks of 4 kilobytes, that is the page size, and each of this is done separately, right. And furthermore, each of this process would have its corresponding process page table, right, which tells how the process is essentially mapped to DRAM. So, now I am essentially having one DRAM, right, but this DRAM can essentially holds the data, the code and data for multiple different processes, right. And the process page table for each of these processes show how the mapping from the process's virtual address space to the corresponding DRAM page is essentially done, right. So, for instance, if I try to access a variable in process 1 which has happened to be at, say, location, or which has happened to be, say, at page frame 1, or which happens to be in this particular block 1 in process 1, right? The memory management unit would then map this into the 14th page frame, right, which is essentially this one, right. Now, in process 2, if I have the same type of variable at the same location, then my memory management unit would map that into another different page frame, which is the 10th page frame. So, you notice that each page frame, even though each process, even though they have different, they could have the same overlapping addresses from 0 to 2 power 32 minus 1, within the DRAM they get mapped to different regions, to different pages. Okay. So, how does this essentially help us? So, with the help of this, we are able to share the DRAM across processes, right. Another aspect which this essentially gives us is the aspect of isolation, because what we say is that the only thing the CPU sees is the virtual address of the particular process, right. So, the CPU can access any address or any data from the location 0 to 2 power 32 minus 1 within the virtual address space. It cannot access anything outside this virtual address space, right. And thus, we can consider this virtual address space as some kind of a sandbox, right. So, everything that happens in a particular application is restricted to this virtual address space. Okay. So, the advantage we get is that if we are having multiple processes running simultaneously or multitasked within a CPU, each process essentially is within this virtual address space sandbox, right. And therefore, process 1 cannot essentially do read, write or modify or access any data or variable in process 2, right, or process 2 cannot read or write or do anything in process 3 or vice versa, right. So, this isolation essentially gives us the security that we want, right. So, for instance, if process 2 was our banking application where we are entering our account number and password, there is no way that process 1 could directly read that password or read the data that you have entered or modify the data, because process 2 is essentially a different process with its own process page table and its own virtual address space. So, this gives us the concept of isolation. Okay. Now, let us look at how shared libraries are managed. Recollect that when we are using shared libraries, we like the libc, we wanted only a single copy of this library to be present in the DRAM, although each process may be using the same functionality. For example, over here we had printf invoked by multiple of these processes, but what we want in order to prevent or not waste space is that only one copy of printf should be present in the DRAM. So, let us see how this works with the help of virtual memory, right. So, what we do is that we essentially have our copy of printf in one particular page frame. So, page frame 8 in this particular example has our library, right, or a part of our library, which essentially holds the printf function, right. Now, what we do is wherever we want to invoke printf, right. So, we use this process page table to essentially map into this 8th page frame. So, here for instance, in process 1 in page frame 5, right, would essentially have some function, say I can invoke printf, yeah. So, in this page frame in this block 5 I can have printf, right, and my process page table maps 5 to the page frame 8, right, which is essentially the glibc library having the printf, right. So, what does this mean, right? So, similarly my block 2 over here is mapped to page frame 8 by the process page table and therefore essentially gets mapped to the library. Similarly, in this process 3 we have again the block 2, yeah, mapped to page frame 8, which is again corresponding to the library, right. So, what we essentially see over here is that even though there are 3 processes, with the help of this process page table mapping, we are able to just have a common code or a common a library which holds just a single copy of printf. So, it is not needed to have 3 copies of printf because printf is invoked in every process. We are having just one copy of printf, and and we are using the processes page table to map the virtual address space for that particular process to the required page frame which holds the printf, right. So, in this way what we do achieve is that we are able to efficiently share common code like shared libraries in a multitasking environment, so that even though different processes would invoke the same functionality, we do not have to have multiple copies of the same code in the DRAM. A single copy is enough.